Welcome to the lecture on programming NPUs in 2025, where we'll cover NPU architecture, development tools, and language-level optimizations. In this presentation, I'll guide you through the current ecosystem, show how vendor toolchains shape performance, and outline practical workflows that get models from research prototypes to efficient, deployable NPU code. The hardware landscape today is a mosaic. Google Coral, Intel NPU, Qualcomm Hexagon, AMD XDNA, and Apple AIN all ship different memory models, data type ceilings, and kernel ABIs, making portability a toolchain problem rather than a hardware constant. In practice, this means engineers must treat portability as something solved by tooling and abstraction layers, not by assuming a single runtime behavior across devices. Here's a high-level view of the NPU software stack. Frameworks export models into a hardware, agnostic, intermediate representation, then quantizers and graph compilers transform that IR into low-level LLVM-based codegens and vendor runtimes with fallbacks. Vendor SDKs determine where developer control begins and ends, so understanding the SDK boundary is key to successful performance tuning and optimization. Intermediate dialects play a strategic role in preserving optimization hints between front-ends and vendors. Formats like stable HLO, ONNX, MLIR with TOSA, IRE streams and micro-TVM carry quantization info, memory layout, and tiling directives that influence lowering. Choosing the right dialect early is not neutral. It shapes the final instruction mapping, efficiency, and the scope for later hardware-aware optimization. TF-Lite delegates act as routing points that connect a single C++ delegate API to device-specific backends like Coral's TF-OFU Lite microcompiler plus IREE, Intel's OpenVINO delegate, or Qualcomm's QNN delegate. Behind that single interface are cache management policies, fallback logic, and profiling hooks that let a portable application leverage different NPUs with minimal code changes. PyTorch 2 captures models as FX graphs using torch.compile, creating a high-level IR that backends plug into. An optimization stack accepts INT8 quantized modules, performs backend integration, and emits NPU kernels, while dynamic shapes still fall back to CPU. To get full acceleration, developers must freeze models and annotate static dimensions, so the NPU can execute the frozen graph end-to-end. For compiler workflows, JAX users and others map to stable HLO, which feeds IRE or similar compilers to produce RISC-V or hexagon binaries. Execution strategies include asynchronous execution and polyhedral tiling automatically, while developers add annotations for preferred tile sizes or exploit Coral's 256 MAC datapath. The best results come from combining automatic passes with targeted developer hints. When high-level graphs hit performance walls, you must drop to vendor-specific intrinsics and low-level code. Intel's Excel-lib for simmed in fixed-point math, Qualcomm's HVX intrinsics and VLIW tricks, or Coral's MapMul templates and double buffering. Optimization techniques like fixed-point quantization, loop tiling, and double buffering are essential to map compute to matrix engines and reach peak throughput. Benchmarks like NPU eval show the limits of automated kernel generation. Large models still struggle with correctness, and only a small fraction of kernels are reliably produced by LLMs or automated tools. Human-guided kernel craft remains essential, balancing cache footprint, unroll factors, and pipeline depth to squeeze out performance while maintaining correctness and efficiency. The end-to-end workflow from model to optimized NPU code follows 4 steps. Prepare an FP32 ONNX model, quantize and optimize with vendor tools to INT8, compile with hardware-aware passes to emit device kernels, then profile and iterate. Profiling looks at NPU utilization, memory bandwidth, and kernel latency, and you repeat the cycle to meet performance and power targets. Debugging and simulation tools let you validate and tune NPU behavior before and during deployment. Windows ETW traces expose system-level events and NPU activity, Coral offers a cycle-accurate simulator for precise timing modeling, and Siva Nupro Studio couples a debugger with hardware emulation and breakpoints to trace CPUMPU transfers for timing bug isolation. The industry is converging toward a portable NPU representation, driven by standards like SPIR, NNEF, and OpenXLA, with the vision that by 2027, a single OpenIR could enable vendor-agnostic NPU coding. That end state would reduce vendor lock-in, making NPU programming more like GPU programming today and enabling broader portability and ecosystem innovation.